that and see how you can leverage that for your own engineering or science applications. So I will share my screen. Yeah. Uh, Sir, is the screen up? Can you please let me know? Dr. Nanda or others, if you are in the chat, can you please let me know if it is
Uh,
visible? Okay, right. I can see a few
yeah, it is. Yes,
CFES.
yes,
Sure. Thank you so much.
yes.
So we'll continue with from where we left off yesterday. Let me also see if I can access the chat so that the chat window is visible on my end and I can answer queries on the go. Right. So yes, let me put it on presentation mode. Let me actually turn off my camera so that I can save some bandwidth. Uh, yeah. So yes, yesterday we were going through some of the basics of uh, optimization techniques. So we looked at how we can solve optimization problems when it is framed in the form of a curve fitting. So if you have a curve which talks about which maps one variable to another, and if you want to fit a curve there, either unconstrained or constrained, we can do both, right? And then we sort of looked at what are the challenges with the some of the traditional approaches. Uh, Typically, if you have local minima, there's a possibility that your solution will get stuck there. In those cases, we usually take the help of nature-inspired algorithms, for example, genetic algorithms, and we saw an example on how do we sort of use it for Rastringens function. We applied that. Now what I'll do is I will show you how you can solve that problem by using another very popular technique, which is called particle swarm optimization. So let me actually to MATLAB now and take you to the demo. So all these files are there with you, I believe. I shared the link yesterday. Uh, so under demo 3, we will try to solve the same problem which we solved yesterday, but we solved it using genetic algorithm yesterday. Today we are trying to solve it using another approach, which is called the particle swarm optimization. Now, the motivation behind all these algorithms are pretty much the same. We try to combine two approaches to achieve the most optimal solution. One approach is called exploration, the other approach is called exploitation. In context of nature-inspired algorithms, are you aware of these terms, exploration and exploitation? If you are aware, can you type yes in the chat, please, so that I can understand? Okay, great. One person responded yes. Others, are you aware what these two concepts called? Okay, great. That's great. I think it's good that you studied it. So yeah, somebody mentioned a brief would be good. So the idea is two sort of contradictory ideas. So whenever you are trying to explore, you are trying to sort of spread out and search for better solutions. Okay. So in the entire solution space, you don't know what will be the most optimal solution. So what you try to do is you spread out and search every corner. So let's say you have lost your key, right? And you are trying to search and find your key in your house. So what you will do is you will tell every family member, hey, my key is lost. Just try to find it. Okay. So what your family members will do is they will take one room each and maybe search there. Okay. That is the idea behind exploration. Okay. But at the same time, let's say you are almost sure that you have left your key near the dining table. So it makes more sense for you to sort of involve others to find your key around the same space. Okay. Which means you are not spreading out. You are rather looking for your resource in a particular region only. So that is called exploitation, right? So by combining these two ideas of exploration and exploitation, you typically arrive at the most optimal solution. Now, whether you would apply exploration mode or whether you would apply exploitation mode, that we don't know right away, but we can do experiments to find out which one of these would be dominant in your case, okay, in the problem that you are trying to solve. Okay, but nonetheless, only exploration might not give you good results, but only exploitation might not give you great results. So it's a good idea to combine these two and come at a particular solution. Okay, does this analogy make sense of finding key? I just gave you a very coarse sort of an example, but the idea was to sort of understand the philosophy behind uh, how exploration and exploitation works. Was that was that clear? Yes, no? Any response in the chat, please? Okay, awesome, great. So the idea is to either and search for the entire solution space or search in a particular region. Okay, you have to combine these two ideas. So again, this is the function that we are trying to solve. As you will notice here, if I plot this particular function, which is the Rastrigan function, it's a complicated function of two variables. You have x1 square plus x2 square minus 10 into, cos of 2 pi x1 plus 2 pi x2. So this is the expression. Okay. So I'm running this. It will take some time for the optimization routine to run. Since it's a fairly complicated plot, it takes some time to sort of generate the graph for this. Okay. So this is the plot. We saw it yesterday as well. Okay. Uh, it's sort of this non-smooth, very rough sort of a terrain. If I can show you the plot and sort of rotate this here and there, you will see that it's pretty rough. Okay, it's like one of those ice trays that we have in our homes, right? Uh, and probably the local minima lies here at around 0, 0. But the problem is if you are at one of these, the global minimum, the, the, the global minima is at 0, 0, but the local minima is all of these local points. If you use any gradient based approach, there's a possibility that you will get stuck at the local minima, which is why we are using this approach. Uh, now now that we have understood this particular graph, uh, we are starting with an initial point. Okay, from there we will try to create multiple solutions and so on. So how many variables are there? There are two variables, and this is my initial point, which is like 4.5 comma 4.5. Now in the plot itself, if you look here, The point will be somewhere here. Okay, somewhere here. And we want to sort of reach here. How do we reach there? Let's see. Okay. So similarly, uh, similar to what we did last day, we will create another task. To access this task, you have to go to the live editor tab. Under the task option, you can search for optimize. Okay. And this particular task will open up exactly this. So don't worry. The problem that we are trying to solve here is a nonlinear problem again, right? Uh, because the the function that we have here is a nonlinear function. Okay, it's not linear. Are there constraints? No, not as such. What is the solver that we are using here? Yesterday we used genetic algorithm. Today we are using the particle swarm optimization. So this one will be the one. What is the objective function? If you notice, this function is already there. This is the restrictions function, which is there. What are the number of variables? N1, that is 2. And you have the lower bound, which is like -5 and 5. So all the solutions that we are searching for lies between -5 and 5. Okay. So in particle swarm optimization, we define this first. We say that uh, you are only allowed to search within a particular bound. That is a good thing because it restricts our search space and helps us to converge to a better solution faster. So this is the one. So in each iteration, we can also plot the best value. Okay. If we choose that, we can also add the solver options. For example, if you want to look at the swarm settings. So in particle swarm optimization, what happens is there are a swarm of objects which is trying to converge or help you converge to a particular solution. So imagine a swarm of ants or a swarm of insects trying to look for the best solution. And then once it is able to find a decent solution, all the resources are sort of converging towards that. Okay. So you can choose the swarm size and everything. By default, they will assume some value depending on the problem, but on the algorithm side also you can choose multiple things. For example, there are things like social adjustment. There are things like minimum neighborhood or inertia. Uh, you can customize all of these things in the function itself. Okay, you don't have to write a script. Uh, MATLAB will automatically write the script for you. Okay, so now that we have decided this, uh, let's run this. When we run this, this set of code will be executed. So if I run this particular function, this plot will be generated. Okay. So initially it was 9 point something. Now you will notice that it is sort of converging and converging and converging. Okay. So now the best function value is 3.14 into 10 to the power -9, which is, well, practically equal to 0. Okay. Why? Because we are trying to minimize the function. So once you do this, you will see also the progress in the form of a chart. Okay. You will see that the mean value of the function and the base value of function, all of this will reduce. Okay. Now, it's a good practice to look at the best value of the function uh, because that will typically go down and help you in the optimization. And if you notice, the optimization ended because the relative change in the objective value is less than the function tolerance. So what we look at is in every iteration, whether the function tolerance, the value of function, the difference between the value of function is reducing or not. If it almost becomes constant after a while, then we can safely say that our function has uh, our optimization has sort of converged. So if you notice, initially the value was 9, then it dropped to 1, and then finally to 0. Okay. So what is the solution here that we got from this particular approach? The answer that we got is minus 0.2347 into 10 to the power minus 5 for x1, and the x2 value is minus 0.3213 into 10 to the power minus 5. Okay. So these are the values of x and I mean x1 and x2, which is in sync with what we expected, right? We expected the values to be very close to 0, 0, and that was the case. Okay. And it did not take a lot of effort for us to achieve this. Okay. We just, you know, we defined the function properly, kept it in a script file. We decided the number of variables. We just chose the solver, and it did a fairly good job. Okay. But again, if you want to customize things, it can definitely help you later. Okay. Great. So this is how we solve the problem by using particle swarm optimization. Yesterday we discussed genetic algorithm, which was again a nature-inspired algorithm. It's a meta-heuristic algorithm, but this is a different approach, but nonetheless takes you towards convergence. Okay. Any questions regarding what we discussed so far? You can ask the questions in the chat. Constraints are not visible. How to add them? Okay, good question, Dr. Meher. So if we look at this particular script, uh, if you choose it to be, let's say, upper bounds, then you can use the constraint. So here you have an upper bound, right? Lower bound is minus 5. All bounds under this is this infinity. But if you like, let's say, add a lower bound or something, similarly things will be there. So this is how it's. Yeah. Right. Thanks for the question. Any other questions from the participants? Okay. In case there are no questions, I think we will proceed with an interesting uh, extension of what we discussed. Let me actually. So this is the same thing which we are showing via video. What I wanted to rather show you is this one. So let's say you are a researcher, right? What you would like to rather do as an extension of this, as an extension of applying a particle swarm or a genetic algorithm to your optimization problem, is look at the sensitivity analysis of your algorithmic parameters, like the constraints itself. Maybe you want to play around with the lower bound or the upper bound. Okay, maybe you want to play around with the population size. Maybe you want to play around with other parameters which you have control over. Okay, let's say you want to apply a genetic algorithm on a similar problem, and you want to look at uh, whether increasing or decreasing the number of generations has any effect on the final solution, right? Or let's say whether increasing the population size leads to better exploration. So if you increase the population size, you have more capacity to explore the entire space, which is bounded by the lower and upper bounds. Okay? So does that affect your overall results? So that is one question. The another question is whether you want to speed up your analysis in some way. Okay. If you want to speed up your analysis, you might have to deploy your algorithm either to a high performing computing cluster, HPC cluster, or your GPU, or to the cores that you have in a very optimized way. Now, your system should have that understanding which cores of your system are free and accordingly deploy these optimization tasks so that you can reach the solution in a faster way. Okay, and also whether you want to integrate your optimization routine for solving a system level problem and integrate it at a system level. In those cases, if you want to use it for solving an optimization problem, uh, whether you can do that or not, right? So these are the typical challenges which a researcher would face. He or she might want to understand how varying the parameters of my algorithm affects my overall result, how I can speed up my analysis, and how I can do system level integration of this algorithm uh, for any engineering or science application. Right? So here I will show you how one of these things will work if you want to look at designing multiple experiments uh, for this optimization routine. Okay, so let's take the same problem where we took the precision function uh, and the script. So this is my live script. Okay, it had the function precision function. I also defined the initial variables. I decided the bounds. You know, I decided the solver options. What is the population size? Maybe 20. And I can also add other things like how, like for how many generations I want to run this. Right? So this is the function that I wrote. Okay? And I have the script ready with me. Now what I'll do is I have this app called under the app section. You have multiple apps. So it will be MATLAB based, math and stats based. Uh, I already chose I mean, there are things related to optimization as well. In case you want to run multiple, you want to execute things in code, you want to generate the C or C++ code so that this can be uh, deployed to any hardware, that is possible. But here what I'm showing you is the app called Experiment Manager. Okay, this Experiment Manager helps you to design experiments based on changing the hyperparameters of the algorithm. So now I am just creating a blank project, and you can, create any general purpose experiment as well. But let me save a very general purpose one. It will create a folder for the same. Okay. So what for this particular experiment, initially, I will add a description, which is like sweep over population size and maximum number of generations for my genetic algorithm experiment. Okay. What are the parameters? I might want to vary the population size by these values, right? It can be 20, it can be 50, it can be 75, or it can be 100. And the maximum number of generations I want to vary, say from 50 or 100 or 150 or 200. Okay. So there are 4 population size values and there are 4 maximum generation values. In the chat, can you please tell me how many experiments this will generate? I have 4 values in population and I have 4 values in maximum generations. Can you please tell me how many experiments will be generated out of these combinations? What is the number of iterations that I will be able to run based on these values? Any number that you have? Okay, Dr. Mihir mentioned 16. Others? 16? Others? Okay. So yes, both of you are correct. The answer is 16 because for every choice of population size and every choice of Gmax, maximum generations, I can generate an experiment. So there will be 4 by 4, right? That is 16. Okay. So now, okay, not this one, sorry. Let me run this and let me bring you here. Okay. So I chose the values as 50, 100, 150, 200. Now I need to write the experiment function, which will sweep over all these values. Okay. Now it will already give you a template on how to write this. So it will look for the params, okay, the parameter values, which are like the things which you can control, which is the population size and the maximum number of generations. So I just write the script which I got from the genetic algorithm experiment, but I just, instead of population size as some fixed value, I will just write it as params.pop size since it's a variable now. And for max generations, instead of a fixed value, I will write params.gmax, okay, since it's a variable. Okay. So, and I am not interested in the solution as such. I am just trying to look at the objective value. However, if you want to generate the solutions, that is also possible. So I define the algorithm, I define the function. All of these things are already there. I have to format it in that way. Okay. So this is the script. But in the same script, I also have to write the function which is there for the optimization one, which is the residence function. So if it is there in your script, please copy paste that in the single script, which will contain the experiment function as well as the optimization function. And accordingly, change the output values. Here, the objective value is the output. Now, I have defined all of this. There are multiple ways through which I can go through or sweep through these parameters. Okay. So I can sweep through the population size, I can sweep through the maximum number of generations. It can either be sequential or it can also be simultaneous. If it's sequential, then when I'm executing iteration number 1, iteration number 2 will not be executed. So it will complete iteration 1, then go to iteration 2, complete, go to iteration 3, and so on. So you cannot take the advantage of parallel computation of your system if you are going for sequential mode of execution. But if you are using simultaneous mode of execution, then that can be executed in parallel. So let me run this, take the simultaneous one. So it is showing you that executing this in parallel, automatically the parallel processes in your system will be activated. Yes, Dr. Mihir, it is parallel computing. So as you can see, it will run things in parallel. Okay. So multiple of them will be queued and they will, for example, here 1, 2, 3, 4 are getting executed in parallel. So yes, simultaneous is same as parallel computing. If you notice, in multiple cores, they are getting executed, right? And once the cores are free, we are allocating the resources there. So that speeds up a lot of execution. Okay. So I think I got you here. So based on that, they will be completed. So if sequence doesn't matter for you, I would say go for sequential. That will definitely be more, uh, you know, a faster execution of this particular workflow. And this is the script. If you want to remove the plots from them, that is also fine. Okay. We select the number of workers. You can select the number of workers, yes, by choosing the pool size. Uh, so if you have, say, 8 cores, you can choose it to be 6 or 7. That flexibility is also there. Okay. So this is how this works. With it, you can also export the progress in the form of a table in case you are using it for any research work. You want to publish how varying these parameters affect the overall performance. This particular exporting helps a lot with integrating that to your research paper. So in case you want to do sensitivity analysis, this is the app you should go ahead with. This is called uh, Experiment Manager. So from here you will be able to do this. Okay, it will be there in your standard MATLAB installation. Now, what? Okay, before I jump to other examples, so just to do a quick recap, we looked at uh, solving optimization problems using particle swarm algorithm. And then we also looked at if we want to vary some of the algorithm parameters and do a sensitivity analysis, we can take the help of an app called Experiment Manager, where we list out what are the parameter values where we want to sweep over, and we can sweep over those parameter values and create multiple experiments and see how they affect the overall objective function or any performance metric. Great. Any other questions, anyone? Before we jump to the next demonstration. Right. So what I'll do is, so now we discussed how you can apply optimization routines for solving problems where you know the equation. Okay. But in case you are looking at an engineered system, let's say you are looking at, any control system or any other parameters in, say, wireless systems, but you have already built the system level model using Simulink, and you want to see how varying some of the parameters can actually affect the performance. Okay. So this is where we are talking about system level integration of this optimization problems. Okay. So in that case, we can also take the help of similar uh, functions. But first, let me tell you what we are trying to solve. So we have a Simulink model which has an engineering sort of design captured. Let me click on this and show it to you. So this is the model. Okay. Okay. So this is like uh, sort of like a control system, which has a transfer function, you know, and which has the one of the k parameters and so on and so forth. Based on that, I am trying to see whether I'm trying to minimize this particular function called ITAE, which is like the absolute error. Okay. We are integrating the absolute error and trying to find whether we can sort of minimize that. Uh, so these are the parameters. I have HS. HS has HS can be written in this form. It's like TW comma 0 by, which is in the numerator, and TW comma 1, which is in the denominator. So we can write the Laplace version of that as TW by, TW plus S or something like that. And this is the gain variable. Okay. So if we know these, if we can formulate the problem in this way, is there a way to apply similar optimization routines here as well? Okay. So for that, what we will do is we will look at the demo 4 solution. Okay. It will load the task for us. So here, what are the variables? We have the k variable and the tw variable. Okay. We are saying that the value of k will vary between 0 and 6, and initially it will be 3. Okay. Similarly, we are saying that the value of tw will lie between 0 and 10 with an initial value of 5. Similarly, if there are other unknowns in your case, what you have to do, you have to just add another one and set the variable name, uh, define the bounds and the initial point. But just to keep things simple, we are working on a problem which has two unknowns and we want to optimize that. Okay. So what we are trying to do here is we are trying to minimize a certain function. Okay. So here I have a local function which is like cost SLX, and I have the function which depends on these two variables, which is tw and k. Okay. If you want to add separate additional constants here, you can add that definitely. And if that is captured as a local function or a function file, that can be done. Again, I'm trying to keep it simple. So I am not adding constraints here, but that does not mean it can be done. It can be done if you add constraints from this particular option. So the solver which I'm going to use here will be again genetic algorithm. You can also use particles form. And you can also add options on training. Let's say you want to, you know, look at the population size and so on. What am I trying to solve is k and tw. But if I want to plot things out, maybe I want to look at the best fitness value and maybe maybe the best individual value as well. Let's see. Once that is there, I need to solve the problem. Okay. So what it will do is it will look at this Simulink model, and based on these constraints, it will try to come up with the best k and tw solutions. Tw is sort of embedded here in the transfer function of this plant. Okay. If that is the case, let me run this. So this cost SLX function is defined at the bottom. Okay. If you had noticed in the model, there is this ITAE metric, which is like integral absolute error metric, which looks at how much we are doing in terms of how close are we in terms of the most optimal solution. Okay. So it will run. So if you notice here, it will keep changing the k and h's value in the Simulink model itself. Okay. So it will change the k value and the t value. So you will notice that these values will change. And at the same time, you will get to see how the fitness is working. So you will get to see the metrics, as well as you will see this particular Simulink model getting executed in every iteration, so that you can come up with the most optimal values of k and tw. Okay. So if you notice, the tw value changed slightly. It was 3 point something. Now it's 4.88. Okay. Let me enlarge this slightly. It will continue to do. Okay. So similarly, if you want to run Simulink models and you want to optimize that, for example, a very common example of this is using nature inspired algorithms for tuning PID parameters. So KPKI, KD. Similarly, so in those cases, what you can do is you can use Simulink to design the plant and the controller and keep KPKI, KD values and pass it to a similar cost function to sort of optimize this ITAE value or some other metric that you think is a better fit. But nonetheless, these values will change over time, as we can see here. If you notice, this value has drastically changed. We had started from 3 and now we are at 0.4258 seconds or so. But if you notice, the fitness value, that is mean fitness value, is sort of decreasing, which means we are able to find better fits as we move through generations. Okay. Again, it sort of oscillated and gave you this 1.9242 value. Okay. So it will keep changing its value as long as you are not settled to a good fitness value. So feel free to run this as much as possible so that you come up with the most optimized value with more number of generations passing. So if you notice here at this point, you sort of reach like the mean fitness value has reached almost 0, right? Because you want to reduce the absolute error. If the absolute error is very close to 0, that's a better fit, right? Nonetheless, it's still trying to optimize. So what I can do is, if I am satisfied with the fit, uh, I can just stop this. Okay, you don't have to run this for the entire level of for the maximum number of iterations. If you are satisfied with the overall process, you can stop it then and there only. Okay? So it is running now. What I'll do is I'll probably stop this thing. Okay. And you will get the K and T0 value from here. Okay. So if you stop it here and go back to the model, you will see that the K value is 5.7195 and the TW value is 1.242 or 1.2. Okay. So in case you want to apply similar things for Simulink, where you already have a block diagram model of a multi-domain engineered system and you want to vary certain parameters to sort of optimize this, all you have to do is write the cost function properly, which is defined here. Okay. This cost function will run the Simulink model and try to minimize uh, the error metric, and you have to pass the parameters that you want to optimize for. Now, these parameters also need to be in the Simulink model as well, so that it can be identified and accordingly optimized. Okay. So this is how, if you notice, the value of K was around 5.79 something, which is well within bounds, and the value of T was 1.4 something, which is again within bounds. So this is how you apply optimization for solving science or engineered problems uh, in case you have a Simulink model or a dynamic model designed in Simulink for the same. Okay. Any questions from this part of the presentation? I think Dr. Mihir had a question on how this can be done for uh, if you want to vary the parameters for Simulink or these things. We'll only calculate and share the values. will also apply the model. Uh, by applying the model, do you mean the Simulink model in this case, Dr. Mihir? Or it will apply to the model itself, right? The values of k, yeah, it will apply. For example, if you notice here, in the Simulink model, the optimized values of k was applied directly here, right? This is not what we started out with. Similarly, the TW value 1.4242 is not what we started out with. So it will optimize and apply the same values in this particular model itself after optimization. Awesome. Great. So this is how we sort of apply this in case you want to. So we covered the three typical challenges that a researcher would face, right? So we looked at sensitivity analysis by using the uh, experiment manager app. We sped up analysis by applying the simultaneous execution. It took the parallel course on your system. And we also looked at how you can do system level integration in case you have a electrical or mechanical or any scientific system built in Simulink, and you can integrate, embed that in that system, embed the optimization algorithm in that system to come up with optimized algorithm, optimized parameters. Yeah. Okay. Now, I think these were covered. In terms of resources, uh, people also get confused on um, what to use and when to use. So I would say look at the objective function and look at the type of constraints that you are applying. Okay. So if you have a certain objective function, let's say least squares, uh, and you want to apply the linear constraint there. So the name itself will sort of suggest like this is least square L squared linear, right? If it's non-linear, then function minimum constraint, right? For non-smooth or multi-objective problems, for at least non-smooth single objective problems, you can use genetic algorithm. But in case you have multi-objective problems, you can use uh, GA multi-opt, which is like genetic algorithm for multi-objective problems. There is also Pareto search and all of these things. Okay, so this particular slide is sort of a guide for you to identify which function to use when. Okay, and in case you are still confused which to use what, I mean which function to use in what scenario, you can take the help of MATLAB. So in MATLAB, we have this thing called MATLAB Copilot. It was released in 2025A. Now we also have something called Simulink Copilot. So if somebody has a Simulink model, they can use GenAI to get insights from there. So in MATLAB Copilot, you can talk to MATLAB in natural language and it will automatically suggest resources to you. For example, let's say I want to solve an optimization problem where I have linear constraints for and non-smooth objective function. Can you suggest me uh, can you suggest me which technique to use to solve such problems? It will think again, you need internet connection to access MATLAB Copilot. But once you have that, it will think about it. It knows about the MATLAB documentation. Okay. And it will generate the results for you. Okay. So Similarly, can you provide a MATLAB ADMM starter, let's say? So it also gives you follow-up prompts, like what is a good question to ask next. So you can ask it, can you generate a simple script for pattern search? So it will think about it. It will generate a script for you. Okay. So it has taken a very popular like Rosenbrock function. It has defined, linear constraints. Uh, it does not have nonlinear constraints. So what I can do is, uh, I can just create a script out of this. So whatever is written here, right? I can just click here and it will create a script out of this. And based on that, I can run this optimization routine. So I was able to generate like what, around 200 iterations of the same, or 120 iterations of the same, and got like uh, the solution for this. Okay. Again, I did not have to understand how pattern search works. But again, you can always have a conversation with this to understand. But if you prompt it to generate a simple script, it will generate the prompt in the same environment and generate the solution for you right away. So now you can just save this script, and use it for further iteration. For example, here, what you can do is you can use Copilot and ask Copilot inside the script uh, and say that, can you define the script to show the plot of what is this? Uh, Maybe the plot of best fit in each iteration. Okay, and you press enter. So it will generate the results for you. So it will generate the plot and everything. And if you accept this change will be accepted, and then you know you can run this particular thing. So then it will sort of generate the script for you. Okay. So this is one way to sort of do things very quickly in case you have some idea for research or some idea for creating teaching material. You want to quickly validate that. Uh, the Copilot will be a friend for you. You can keep prompting with this and generate results. Just one thing to keep in mind here, you should validate the results before sort of using it in research or rolling it out in your classroom, because it's nonetheless a probabilistic tool. So sometimes it might hallucinate in case uh, you know properly it is not prompted, or it is looking for better context. Uh, Another offering that we have in this space is a lot of uh, nowadays we are using a lot of Claude and Codex and Gemini CLI. So agentic engineering is something which is coming up big time, and industries and academia are looking at how you want to sort of leverage this. Uh, we do have offerings in this space. It's called MATLAB Agentic Toolkit. Okay, I'll just show you the page and I'll paste it in the chat so you can also explore it later. So a MATLAB Agentic Toolkit essentially gives you the plugin or sort of the wire or the cable which helps you to connect a popular AI agent to MATLAB. Okay, So it has something called a model context protocol, which is like the interface between the AI agent, say a Claude or a Copilot or things like those, and it helps you to interface with MATLAB. Now, what we are offering here is skills, which is like recipes for better execution of code. Okay, so if you have access to MATLAB skills, you can write automatically allow the agent to write code for you. Uh, in terms of optimization, also there is a lot that we have. So I'll show you in terms of skills that we have. We have skills around math and optimization. If I click here, so if you click at the math solve optimization, there are all these things, how to sort of uh, tune the solvers or uh, change the function to an optimization routine and so on. If I go to the MATLAB Agentic Toolkit, if you look at the skills catalog, and if you look at optimization, which will be math and optimization, there will be a lot. So feel free to explore this one. Just one thing to keep in mind here is that you need access to the paid versions of these popular tools, which is like Claude or Copilot or any of these ones. Maybe it will be Codex, it will be SourceGraph or Gemini, but you need the paid version for the AI agent. The MATLAB part, the skills part, and the MCP part is free. Uh, all you need to do is follow the instructions which is captured in this particular page, and accordingly you will get access to all of this. Okay, so I think this sort of brings me towards the end of the session. So just to do a quick recap of what we did, we initially started with meta-heuristic algorithms like PSO, and we saw how that can be applied to solve problems. We then saw how varying the algorithmic parameters or the hyperparameters of the PSO can help you to generate multiple experiments using experiment manager. We also saw how you can integrate these optimization routines into system level integration, especially if you have any engineering or science applications. If you have a Simulink model for that, you can write the cost function accordingly so that the Simulink models can also be updated by tuning the parameters. And finally, I showed you how uh, you can leverage GenAI and agentic AI by using MATLAB and Simulink, right? So just a few final resources before we wrap up. Uh, there is this thing called optimization on ramp. Okay, it's a free course. All you need is a MathWorks account to explore this, and it will take you through the basics of optimization in MATLAB in 1 hour only. So what I'll do is I'll just show you how this looks on the web page. So if I bring it here, this is the self-paced online course that we have. Okay, uh, it will take you through an introduction and how do you solve an unconstant optimization problem, constant optimization problem. Uh, Also apply your knowledge to an optimization project that will give you some hands-on experience. And finally, it will conclude with some additional material for you to explore. So this contains practice sessions as well as illustrative videos. So it's not monotonous at all. It's very interactive, and you can just solve different tasks to sort of proceed from module 1 to module 4. Okay, so I will paste this one as well in the chat. Please feel free to bookmark it. If there is any sort of homework that I can give to you, that would be completion of this particular on ramp. It barely takes you 1 hour, but makes you familiarized with optimization routines and optimization workflows and how to apply them using MATLAB. Okay. Uh, by saying that, I will conclude today's session. But before that, any questions that you have? Uh, what I'll do is I'll also turn on the camera. Dr. Mihir has his hand raised. Dr. Mihir, can you unmute and let us know in case you have any queries?
Good evening, sir. Am I audible?
You are audible, sir. Please go ahead.
So, first of all, I'd like to thank you for this wonderful session. It was
Right.
very knowledge imparting and it's very user friendly as well. I have a question for you is, let's say if my system is taking too long to run, let's say I have an optimized
Right, right,
2.5, 3 days to run the entire process and
right.
then generate the values. And if I'm using this particular system, I probably think that it would bring down my time drastically. But let's say in the existing system also,
Hmm.
uh, I'm not able to online because if you're not there for, I presume 15 to 30 minutes, it logs out on its own.
Hmm,
So is
hmm.
there keeping my PC engaged for longer working hours, as well as it's this out on a shorter span of time.
Hmm. So I would say if you are using parallel pool, that will speed up the process definitely. Uh,
Sir, I'll add more to this. I have
yeah.
already used parallel pool here. I'm using
Right, right.
64 workers here already.
Okay,
Come down to 2.5 days. Prior to that, it was going around 6 days for one,
okay,
enter.
okay. Uh, is the optimization function or the uh, problem that you are trying to solve, is it very complicated? Does it contain like a simulating system or how is that,
It's
sir?
it's uh, sir. It's basically what I feel is it's taking the it's putting the values into the simulation, calculating it, again fetching those values back, and then again putting it back. That is what is taking a longer time. That is what I presume. So from workspace to and code to again the workspace back to the simulation. I think this is
Hmm.
something which is increasing my time lap. That is what
Sure, sure, sure.
should be the
You can
issue.
understood, sir. Uh, yeah, it would be good if you can write to me, sir. Maybe explaining the
Sure,
problem
sure.
that you are trying to solve and everything. Uh, because I think you are from Charusat currently, sir, if I'm not mistaken.
Yes, sir. Yes,
And
sir.
I believe
Yes, sir.
Charusat already has access to the campus, right? So I will also try to see if my Pune team members can also reach out to you regarding this. But please feel free to write to me, sir. I'll also I think we are already connected via LinkedIn, but I'll
Yeah,
still
yes, yeah,
I think it would be good if you can send me an email. Then I can look
for
into
sure, sir.
this for sure. Sure. Thank you so much for the
Thank
questions.
you so much, sir.
Yeah,
Thank you for your time.
sure, sure. Great. I think I'll turn on my camera also since we are. So, but good interaction today overall. Thanks for the questions. And uh, what I'll do is now I'll stop sharing.
Yes, thank you, Pratyush Royji, for taking wonderful two sessions and explaining the genetic algorithm and particle swarm optimization, how they can be effectively coded using MATLAB platform, along with the variations of parameters and everything, all aspects you have covered. And participants are also very, very active and asking queries.
Yes,
So that is the actually beauty of the FDP, that it should be
yes,
very, very interactive,
yes,
especially the lab sessions. They are always interesting.
yes.
So we are thankful and expecting future collaborations also with you.
Sure, sure, sir. It
Yeah.
was. I think it was a pleasure. I think now it's 8:15 now, and I still see. 45 participants in the call at this moment. It's very warm to see this response. And thank you for the support regarding this particular FDP. Uh, and thanks everyone for being so patient. In case you have any queries, please feel free to reach out to me on mail. I'll be happy to share more resources with you. And I will anyways write to Dr. Nanda and share all the resources that we have discussed over the past 2 days. Um, I hope that will be beneficial
Sure,
for
all
you
the
in your future.
resources we will be sharing with the
Sure,
participants.
sure. That'll be great.
Sure. Thank you.
Great. Thank you so much, sir. Thank you everyone for joining. Yeah. Have a nice rest of the day.